Professor Michelle Gemmer received her PhD in condensed matter physics from Northeastern University in 2015. She then went on to a NRC postdoc position at NIST. And after starting at the Naval Academy in 2018, she has studied a variety of magnetic materials that have a unique spin structure. Today, she is going to give a talk on decoding the magnetic properties of helical spin spirals. Thank you very much, Michelle, for accepting our invite, and the floor is yours.
So thank you so much for that introduction. Thank you so much for having me as a speaker for this event. And I'm going to tell you about a material that I'm super excited about. And I hope that by the end of this talk, you'll also be excited about it. So I'm currently at the Naval Academy, but this work was done in conjunction with many other people. So at United States Naval Academy, we only have undergraduate students that are training to be officers in the Navy. And so the majority of the undergraduates involved in this work have already graduated, and now they're either ensigns or lieutenants in the Navy. We also have my PhD advisor, Don Hyman, active in this work. A lot of the support comes from the Laboratory for Physical Sciences with Dr. Greg Stephen and Adam Friedman. And it's been a huge collaboration that we've been working on since 2020 to really try to understand the material system that we're going to be talking about today. So I'm going to mostly be talking about iron 3 gallium 4, which is a mostly forgotten compound. So it was originally studied in the 1970s and 1980s because it has multiple magnetic transitions. And these magnetic transitions were curious in nature, and they were easily tunable with the addition of dopants. So a lot of the work that was done in the 1970s was looking at how the metamagnetic transition changed from around 60K and how to actually increase that metamagnetic transition. But then the work kind of fell out of favor because it was such a unique compound and no one really truly understood the full mechanisms of why we have multiple metamagnetic transitions. So in this work, this is the iron 3 gallium 4 lattice, and it's a monoclinic structure with 4 unique iron sites. So the work that was published in 2015 by a group in Louisiana, they started to bring in some single crystals in order to study what is the actual magnetic structure. So as you can see in this right-hand side of the slide, there's, due to the multiple iron sites, the spins can behave differently along each crystallographic axis of the monoclinic structure. So the helical spin spiral is almost like a two-dimensional spin. The transverse canonical spiral is whenever it's rotating and precessing around almost like a cone. And similarly, the longitudinal spin spiral structure is like a cone, but in the opposite direction. So we're going to be looking at these 3 different states of the magnetic spins as a function of temperature and as a function of field. The other reason why this is very interesting is because it displays metallic behavior, and we'll get into that in a little bit. So the majority of the work has already been published in the manuscripts that I'm going to be talking about. So the first one was in 2022, Journal of Alloys and Compounds. So we were able to figure out how strain affected the lattice using arc melting, because at every single annealing condition, we had a slightly different strain. So we were seeing that we can tune these properties with basically adding strain and pressure. The other one that we published in 2022 was based on the single crystal work, and it's the helical spin ordering and room temperature metallic antiferromagnetic iron 3 gallium 4. So these are 2 of the main resources if you want to look into this a little bit further. So in the single crystal work, what we saw is we were growing the crystals using a 2-zone furnace and having iodine and a ratio of iron and gallium, and we were able to grow the single crystals along the B-axis. So the long axis is the B-axis, the A and C are related to the facets that you see in the crystal. So after we grow it, it gets about we can get really large crystals that are almost 800 microns, but we want to keep them a little bit smaller since around 600 microns, they tend to twin, as you can see on that little surface right there. So in the single crystal work that was published in 2022, we were able to find the magnetic behavior along each individual crystallographic axis. So in the graphs, what we have is when the field is parallel to the B axis, the A axis, and the C axis. So as you can see, the magnetic properties, they change a little bit in terms of their inflection points along each crystallographic axis. And while there's different inflection points, maybe slightly different features, essentially it has the same magnetic behavior. Whereas you increase the magnetic field from when we go from low field to high field, we're actually suppressing the transition. So as you can see at low field, we have this metamagnetic transition, or low temperature, we have this metamagnetic transition that actually increases whenever we apply more magnetic field. And then in the upper range, around 360 Kelvin, we have the secondary magnetic transition that is actually being suppressed as we increase the field. So we can take a quick look at this magnetic phase diagram in order to see how the spins are oriented. So at low field, low temperature, we have this first ferromagnetic phase. In this intermediate temperature, we have a helical spin spiral state where it could be the helical spiral, the transverse canonical spiral, or the longitudinal spiral. Whenever we get to high enough temperature, we introduce a secondary ferromagnetic phase, and we see that the spins reorient with temperature and field. And we have spent the last couple of years trying to understand what is the mechanism behind this. So we're trying to understand the magnetic ordering, and we can take a quick look at the magnetization versus field graph along the A, B, and C axis, which are noted by red, black, and blue. And what we see is at low field, we have this linear contribution along the B and the A axis, which is related to the helical spin spiral state, where we can imagine we're applying a field and we're causing the spin to rotate. After about 0.7 Tesla, we start to enter the another spin spiral state, the transverse canonical spiral, and we start to get extra inflection points as we increase field, which is related to basically reorienting the spins, kind of similar to a spin flip or spin flop transition, but not quite. And then along the C-axis, which has different behavior than the A and the B, we have the longitudinal canonical spiral where it behaves linearly with field up to about 1.5 Tesla. And then after the single crystal is saturated, it goes into this ferromagnetic state where all the spins, you can imagine that they're aligned. But as you increase the field, you're going to get spin reorientations, and you're going to see different inflection points based on those spin reorientations. So we can compare this to a spin flip and a spin flop. So if you were to look at the schematics for the spin flop, what you see is if you have an applied field, you'll have a critical field at a certain magnetic field where all of a sudden you'll have a drastic increase in the magnetization, and then you'll have this spin canting effect. If you were looking at it along the opposite direction, what you'll see is that it behaves similar to the C-axis, where you have the applied field, where it behaves linearly up until an inflection point where it becomes saturated. Spin flip looks somewhat similar. It's just based on how your transition is actually ordered, whether you or not you have extra inflection points from the spin flip to the spin flop. So if we were to look at the field parallel to the B axis, what we'll see is that at different temperatures, it behaves differently. So what we see is at 30 Kelvin, even along the B axis, it starts to look like that linear magnetization up into this inflection point, and then it saturates. And as we increase the temperature, we see the changes of the inflection points through the helical spin spiral state. So if you remember, whenever you're below about 68 Kelvin, you're in that first ferromagnetic state. Whenever you're above that 68 Kelvin, that's when you're starting to get the anti-ferromagnetic ordering. So we can kind of compare this to a spin flop based on how the magnetization looks. So whenever we're talking about the resistivity of the compound, it's interesting because we do have an antiferromagnetic-like state, and what we have is that metallicity is not prohibited. So it's interesting to look at these antiferromagnetic metals because they're being proposed for various applications. And what we see here is using DFT in either the ferromagnetic or the helical spin spiral state, we still will have something that looks somewhat metallic. And what we take a look at the resistivity versus temperature graphs, we see that we do have the increase of the resistivity with temperature that's indicative of a metallic-like material. And what's interesting is when you take a look at the resistivity or the resistance graph in this case, you can see right where the transition from ferromagnetic to the helical spin spiral occurs by looking at this little discontinuity around 70 Kelvin or so. And you'll see that the transition is slightly different between the A, B, and C axis due to the differences in how the magnetization is ordered. So the majority of the data that I will be presenting was done at the National High Magnetic Field Laboratory in Tallahassee in collaboration with Dave Graff. And we used the superconducting magnet SCM6, which is a PPMS. And we did that so we could use one of the cells that would be able to actually fit a crystal this size because the crystal is actually extremely narrow. So we took a look at the magnetotransport in order to try to figure out different, why the spins behave a certain way along different axes. So we took a look at the magnetotransport where you apply magnetic field, you compare it to the initial resistance, and then you divide out the initial resistance at 0 field. So everything should be normalized at 0 Tesla to be 0. So this is a little normalization procedure. And what we have is the A-axis is in red, the B-axis is in black, the C-axis is in blue. And at T is equal to 2.6 Kelvin, where we're in that ferromagnetic state, what we see is a sharp increase of the magnetoresistance at before 0.75 Tesla. And then we start to see kind of like a parabolic or type curve. The C-axis, it kind of dips down to slightly below 0, but then it increases like cyclotronically. And then the A-axis looks pretty similar to the B and the C kind of combined. So 0.75 Tesla is right where we have that spin change, spin reorientation along the A and the B axis, which persists throughout temperature. So we analyzed the data looking at the resistivity in the low field and in the high field. So in the low field, we used a mu times mu naught h. Mu naught h is just the applied field raised to the q power, where q is between 1 and 2. So you can kind of think about this as a quadratic based model that's slightly different from the higher field data. So we use the quadratic model, which is typical of SD scattering in the electronic orbitals. And whenever we see that the field is parallel to one of the regions, it increases one of the spin fluctuations in one dimension, but also decreases the spin fluctuation in a dimension that's perpendicular to it. So whenever we are looking at this type of scattering, what we notice is that we do see this huge increase in the B-axis, but the C-axis is somewhat suppressed, which is standard to this model for SD-type scattering. So this is also known as the Rivier's lattice model that you can look into if you're interested in looking at the different types of transport. For the high field, it behaves similar to how all metals behave, which is an electron-magnon contribution, which was first really published by Koshla and Fisher. And what we see here is that it is electron-magnon scattering. We have terms that are also proportional to the applied field mu naught h squared, and that is going to be related to the mobility of the material. So the positive magnetoresistance along this A and the C axis in particular, and along the B axis at high field, is just typical orbital cyclotronic behavior of metals. So what we see is that at the data at other temperatures, for the 2.6 Kelvin, which is the data that I just first showed you, we see this huge increase of the magnetoresistance along the B axis that is somewhat different. And then after the critical field for the spin flop transition, it starts to behave kind of like a normal metal. Whenever we get up to 20 Kelvin, where we're still in that ferromagnetic state, we still see that big increase. And then we start to see more negative magnetoresistance, indicating that, hey, it looks like a metal. 50 Kelvin, that is going to be the temperature right before we hit the transition from ferromagnetism to the helical spin spiral state. And we start to see that we have a large negative magnetoresistance at higher fields, again, indicative of metal. But we do have this anomalous positive magnetoresistance along the B axis at all of these temperatures. So what we note here is that we have a positive high field magnetoresistance dies out quickly as the ferromagnetic saturates, but this low field contribution still is sustained. So if we were to take a look at 75 Kelvin, that is the temperature that's closest to the ferromagnetic antiferromagnetic transition. And we just start to see that our positive magnetoresistance along the B axis dies out. So it's still there at when you are in the antiferromagnetic state, it's just much smaller. So if you take a look at the inset along the 100 Kelvin data, it still exists along the B axis, and then it actually starts to occur also along the A axis because now they're in similar magnetic states. So while it's smaller, it still persists. So now if we were to take a look at all temperatures along the B axis, just so this way we can kind of take a look at what it looks like holistically, the blue curve is 2 Kelvin, the black curve is 75 Kelvin, and the stuff in between the two are going to be basically all Earth temperatures. So what we note here is that the magnetotransport along the B axis is super interesting because not only do you have that positive magnetoresistance up till 0.75 Tesla for almost every single temperature, what you also have is a little discontinuity along the magnetoresistance. That's a change in the resistance state. So where we see that there is an increase and then a sharp decrease in the magnetoresistance, that's actually where you're in the transverse canonical state. So it actually causes a huge change in how your electrons are moving through the material with applied field after you are in that antiferromagnetic state. And then right where the area of lower magnetoresistance drops out, where you start to see that increase again, that is where the magnetization saturates again. So that's when you're in that ferromagnetic state after you hit a certain field. So if we were to take a look at the lower resistance state and compare it to the magnetization, what we see for the lower resistance state, it's going to be the area between 0.75 Tesla and where we see that saturation peak. And this graph to the right actually shows we have this persistent magnetoresistance step at 0.75 Tesla, which is related to the dark black curve. And then right where it saturates, where we have that little increase again in the magnetoresistance, that is where we actually have the saturation field. And you can see that it behaves pretty similar to each other. So if we were to take a look at the magnetoresistance along the C-axis, which is where we're actually suppressing the scattering, what we'll see is that it behaves pretty similar to a metal. In general, we only really use the high field model developed by Kochler and Fisher, and it behaves pretty well, especially after about 2 Tesla. What we do see is that we do have this area of suppression related to the critical field along the B-axis, but it's interesting, but it's not all as interesting as the B-axis, which has really given us a lot of insight into where the transverse canonical spiral occurs. And then if we were to take a look at the A-axis is actually a little bit of a mixture of the B and the C, where we do see that suppression at low temperatures before the material enters the helical spin spiral state. And then we start to see that whenever it enters the helical spin spiral state, we actually do see a positive magnetoresistance that scales well or similarly to the B-axis. So the positive magnetoresistance is one of the big things to take away from this talk, which is kind of rare in a lot of these antiferromagnetic materials because it's related to a super large mobility. So if we were to look at a ferromagnet, the ferromagnet materials normally caps out at around 50 centimeters squared per volt seconds. What we're seeing along all temperature ranges using our fitting model, where mu is related to the mobility, which is plotted in one of the plots to the right, what we see is that we have a large mobility at low temperature, which is again where it's in its ferromagnetic state. The gray line notes where it enters the antiferromagnetic state, and what we see is that we still have a quite large mobility for something that is not particularly magnetic at that point. So what's also interesting is that if you were to look at the data between 150 and 250, the A and B axis have almost the same mobilities. So for the high field data, whenever we're taking a look at mu, B1 and B2. This is also related to mobilities, and they're also in centimeters squared per volt seconds. As we can see here, especially for the mobility that's related to a similar term in the slide prior, the B squared, we have something that is extremely large. So we see that the mobility levels out at around 300 centimeters squares per volt seconds, even in the antiferromagnetic state. So we notice that the mobility doesn't really drop down as we increase temperature, which is a little bit unique for a material. So what we see is that we have a much larger mobility than a typical ferromagnet by a factor of 100. And what this really indicates to us is that the ferromagnetic state is not actually a traditional ferromagnet. So by using the magnetotransport data, we always were thinking that this ferromagnetism that we note in the low temperature range, it's not quite a true ferromagnet. It just behaves kind of similar. Even if you were to look at the magnetization curves, what you'll note is that you have a strong linear slope to the magnetization and then a sharp saturation, which is a little bit unique. And so what we can really start to think about here is the magnetoresistance versus spin state. So to the left, I have data at the 200 Kelvin temperature, and to the right, I have the magnetization data at 210 Kelvin. Both of these are the B-axis. So the black is the B-axis on the left, the right is the B-axis only plotted. So what we see here is that when we're in this low field state, what we have is that we have almost randomized spins leading to a low magnetic signal. As we increase the field, we're starting to cant the spins. So this way they start to rotate a little bit closer together. And then after about 1.5 Tesla, we have something that behaves like a ferromagnet. So what we can note using the same kind of idea is that low field, low temperature, localized spins with large fluctuations, which increases the magnetoresistance signal while suppressing that in the C-axis. And then whenever we're in this intermediate state between 0.75 and about 1.5, we see more ordering, but a decrease in the magnetoresistance. And then at the high field, we see ferromagnetic type ordering. So hopefully I convinced you that this is an interesting compound. The positive magnetoresistance persists almost to room temperature, and it behaves like a localized electron model. And what we notice is that the magnetoresistance really shows how the ordering affects the electronic properties of the material. So in addition, there's also the super large mobility, which at low field, low temperature, that is not necessarily a traditional ferromagnetic state. And what we notice is that there's a strong anomalous behavior below the critical field if we were to compare this to the spin flop transition when the B and the A axis are both in the helical spin spiral state. So these are the publications that we have already published. There's been one published about a thin film that the collaborators that I work with at NRL and myself put out recently, and there's going to be even more publications. So thank you so much for your time and attention. Again, thank you to everybody that has helped work with me on this project. And it was nice being able to talk to the members here today.
Well, thank you, Michelle, for the very nice talk. Now the floor is open for questions. You can either unmute yourself and ask, or you can write the questions on the chat.
Hi, Michelle.
Hi.
I have a question. Yeah,
Yes.
I have a question. So you mentioned that the mobility in this single crystal iron gallium is extremely high. But I want to know the reason why it's so high, because although you said that it's not actually ferromagnet, but in one figure you show that it's actually saturated at around 2 Tesla. Actually, it has some, I believe, ferromagnetic behavior. So I want to know how the mobility, because in generally ferromagnetic material, the magnon-electron scattering causes the mobility to decrease.
Okay,
what's your thought there?
Okay, so just to make sure I understand the question. So even whenever it's not in the helical spin spiral state, why is the mobility so large?
Yes.
Okay, so I think a lot of it has to deal with the chiral spins. So whenever you're working with helical or chiral spins, I kind of use the two terms interchangeably, but it's probably better for me to say helical. So similar effects have been seen in systems with known chirality, like iron, silicon, and I think manganese, germanium, if I'm not mistaken, which show kind of almost skyrmionic behavior. Now, I'm not claiming skyrmions because you don't shout fire in a movie theater and you don't shout skyrmions in a magnetism talk, but it's something related to essentially, I think, the processing of the spiral. Now, I really wish I had a better answer for you than that, but unfortunately, I think that we're still in the midst of the studies about what is the mechanism to really cause that super high mobility. Right now, we're just reporting the effect.
Thank you. One more question. So actually, we work on thin film, so we are very interested in making these very novel material as a thin film structure. So, do you have any substrate in your mind which can be used to fabricate thin film of this material?
Yeah, so in our most recent study that was published with, I believe Joe Prestigiacomo was the lead author on this, and I think Steve Bennett was the last author on this. I'm the second author on it. The films were grown on STO, so strontium titanate. So I think that was seen to be the best substrate, but the great news about this material is that it is thermodynamically stable. So you can technically grow it on any substrate, you just might have a secondary phase, unfortunately. So you can still grow it on silicon. In order to get a really nice thin film though, I think STO is needed.
Thanks. Thank you, Michelle. Thank you. Very nice talk. Thank you for the talk.
Thank you.
So we still have time for one quick question. So if there are no further questions, maybe we can thank again Michelle for the very nice talk.